Okay, so now that we're getting comfortable with the octet rule, we got to talk about the exceptions to the octet rule, right? Because you knew that was coming. Exceptions, everything. So there's three broad categories of exceptions. Free radicals are molecules and ions that have an odd number of electrons in their Lewis structures. If you've got an odd number of electrons, it will be impossible to draw a Lewis structure where you have an octet or a duet for everyone, because that involves things being in pairs, and you can't do that with odd numbers of electrons. So free radicals tend to be very reactive and unstable, and that's why free radicals are bad for biological organisms, because they tend to react, and they react in ways that aren't good for you. So things like vitamin C and other antioxidants will help to get rid of the free radicals, and that's why they recommend those. So let's draw a Lewis structure for one of my favorite molecules. No! Nitrogen monoxide. You guys aren't going for that joke anymore. Oh, yeah. We're over that one. It's fine. I don't tell them for your amusement, I tell them for my own amusement. Okay, so nitrogen has 5 valence electrons, oxygen has 6, that's 11, right? So let's do our best here. We've got 2, 4, 6, 8, 10, 11. Well, there nobody has an octet, that's not cool. If we make a double bond, then we could get at least one of them to have an octet, right? So let's move one of these pairs from the nitrogen and make it a double bond. Now the oxygen has 2, 4, 6, 8, and the nitrogen has 2, 4, 6, 7. So, Is there another possibility, though? What if we put the lone pair on the oxygen, that odd electron on the oxygen, and give the nitrogen the octet? That's possible too, right? So we have these two possibilities. The Lewis model doesn't handle this well. So all we do is we do the best we can. You draw the best Lewis structure you can, and we're going to put that odd electron in there to minimize the formal charges. So we need to consider formal charges to decide which of these is a better structure. So here, the nitrogen, if we're looking at formal charge, nitrogen brings 5, and it leaves with how many? 1, 2, 3, 4, 5. So the nitrogen here has a 0 formal charge. How about this oxygen? It brings 6, and it would leave with 2, 4, 5, 6. So 6 minus 6 is 0. So for this structure, they both have 0 formal charge. We're not going to be able to do better than that. Let's just check this guy. For the nitrogen, 5 minus, how many electrons would the nitrogen be taking? 6. So that's going to be a negative 1 formal charge. And the oxygen brought in 6 and leaves with 5. So that would be a positive 1. So which is the best one? The first one. This is the best one. So sometimes they'll ask you to draw all of them. Sometimes they'll ask you to draw the best one. Sometimes they want you to draw all of them and say which one is the best one, or draw all of them and put formal charges on them. There's just a lot of variations. Any questions? Odd electrons. Another type of violation of the octet rule is when you have an incomplete octet. You have less than 8 electrons. And there are some elements that do this. We already know about hydrogen. Hydrogen makes a duet. And we say, well, that's because he's so small, he's in the first period, we'll let him slide on that. There's a couple of other small atoms that also do less than 8 electrons. They tend to do 6. And boron is one of those. And let's just look real quick. What would be the Lewis structure for the atom boron? How many valence electrons does boron have? 3. 1, 2, 3. So what I told you earlier is that, we look at this and we think, well, boron probably wants to make 3 bonds. And it does. And it's not going to have a lone pair, and it's going to be okay with that. So drawing a Lewis structure for boron trifluoride, boron will be in the middle, and the fluorines around the sides. And then we've got a total of 24 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Got the right number of electrons, but we don't have an octet on boron. What are the formal charges here, though? Fluorine likes to form one bond. It's got an octet with one bond. You can do the math. All the fluorines have 0 formal charges. What's the formal charge on this boron? 0. It brought in 3 electrons. If we cut up all the bonds, it will leave with 3 electrons. This is the correct structure. So why not a double bond? Could we draw it with a double bond and have the octet rule? Sure we could. I'm going to take that pair because that didn't come out very well. I'm going to share that with the boron so that now everybody has an octet. Well, we didn't mess with these 2 at all. Those are still 0. But now what's the formal charge on this fluorine? It has 7 electrons to start with, and in this compound, cutting the bonds in half, it's going to leave with 6, right? A positive 1 formal charge. And the boron started with 3, it's going to leave with 4, it's going to have a negative 1 formal charge. That's worse, right? And to make things even worser, more worse, badder, more worse. Here we've got the negative charge on the boron when fluorine is the most electronegative element. So this is just like not good. So we don't want to do that. We want to keep it like this. So boron often will form an incomplete octet. This compound is fairly reactive, and it will react with other things in a way that does complete the octet on boron, but boron trifluoride does not have an octet on boron. So it's not that boron never does an octet, but sometimes it doesn't. Use formal charges to tell. Beryllium has 2 valence electrons. Beryllium also tends to have incomplete octets. So again, it's the little guys that are violating this. We don't talk about lithium because lithium only forms ionic compounds, so we don't have to worry about that. And helium, we don't talk about helium because helium doesn't form any compounds, so we don't have to worry about him either. So we've got odd electrons, we've got not enough in the octet, and then we can also have too many, more than 8. So this happens with elements in period 3 and above, or actually, it makes more sense to period 3 and below. Period 3 and periods with a number larger than 3, 4, 5, 6, etc. These can expand their octets. They can go up to 12, 10, 12, or 14. So let's look at arsenic pentafluoride. So we're going to put the arsenic in the middle, and we're going to put the fluorines around the sides. That wasn't very good. And then we're thinking, well, there's a 5th one. I'll just have to tuck it in here. And if you count up all the electrons, you can do it like this. And that's the correct number of valence electrons in the Lewis structure. These fluorine atoms are all very happy. They have octets, they have one bond, 0 formal charges. Let's look at that arsenic. Okay, what group is arsenic in the periodic table? It's in group 5, right? It has 5 valence electrons. If we cut these bonds in half and dissolve this molecule, how many electrons would arsenic leave with? 5. So its formal charge is 0. It's violating the octet rule, but it's okay. The reason it can do this is arsenic has valence electrons in the 3s and the 3p orbitals, right? The 3d orbital is just a little bit higher in energy, and so it can actually, what happens is it expands into the 3d orbitals to make the extra bonding orbitals. Things like carbon and nitrogen with valence electrons in the 2nd energy level, 2s, 2p, there is no 2d orbital for them to expand into, and so they can't do it. Sulfur hexafluoride. All sulfur in the middle, and fluorines all around. There's 4. I'm going to squeeze in 2 more. And then you can count those electrons. I'm tired of counting by 2. It gets a little crowded in here. Each of the fluorines has an octet with 1 bond, 0 formal charge. What about the sulfur? Sulfur has 6 valence electrons. If we break those bonds in half, it will leave with 6 electrons. It also has 0 formal charge this way. So those are expanded octets. Any questions? Let's look at sulfuric acid. So here, sulfur's in the middle, and there's going to be oxygens around it. And the hydrogens are actually going to be on the oxygens. You might say, well, how should I know that? Well, you'd have to do some trial and error. One thing that does make sense, though, is if I put the hydrogen on the oxygen, now this oxygen is going to have 2 bonds. That's what oxygen likes. And these oxygens don't have 2 bonds, but I can't help them right now. Total number of electrons. We've got 2 hydrogens, that's 2 electrons. We've got a sulfur, that's 6. And we've got 4 oxygens, I think that's 24. And so that's what, 32? So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Yay, right? We got octets for everybody, except hydrogen, who doesn't want one anyway. Let's look at the formal charges, though. So we don't have to think about hydrogen. We have 2 different kinds of oxygen here. This oxygen and this oxygen are in the same situation. They have an octet with 2 bonds. Those are going to be 0 formal charge, right? This oxygen and this oxygen are in a different situation. Octet of electrons, but only 1 bond. So they're going to have a formal charge. So for those oxygens, they brought in 6 electrons, and they're leaving with how many? 7. So they're each going to have a -1 formal charge. So this one's -1, this one's -1. What about the sulfur in the middle there? It brought 6 electrons, and it would leave with 4. So that's a +2 formal charge. You might say, well, that's too bad, but what else can we do? We can expand the octet on sulfur. Sulfur's in period 3, it can do that. It's big enough. This negative formal charge tells me that in this structure I've drawn, oxygen has too many electrons around it. And this one has too many, and the sulfur doesn't have enough. So I could take one of these lone pairs and make a double bond with the sulfur. And that would make the oxygen happier, because then it's got an octet with 2 bonds. So let's do that. Get rid of that and take one of these. This is going to alter that. And I'm going to make that a bond. I just moved a pair of electrons, that's all. What's the formal charge on this oxygen now? 0. It has an octet with 2 bonds, it's 0. So that's not working anymore. Now, what's the formal charge on this sulfur? Instead of getting 5 electrons in the split, it's going to get, instead of 4, it's going to get 5, right? Because we're cutting the bonds in half. So it's going to get 1, 2, 3, 4, 5. So now it's a +1. So that made it better, didn't it? What if I did the same thing down here? Took one of these lone pairs and did a double bond with the sulfur. So I'm going to move a lone pair. Now, this oxygen has an octet with 2 bonds. You can do the math. That's a 0 formal charge. What about the sulfur? Well, sulfur brought in 6, and now it would leave with 6. So the formal charge would be 0, right? 6 minus 6 is 0. This is the correct Lewis structure for sulfuric acid. Sulfur expands its octets to lower the formal charges. So period 3, period 4, 5, 6, 7, that can happen. Period 2 elements, never, ever. They have nowhere to expand. Any questions? Okay, practice. Write the Lewis structure for xenon tetrafluoride. Well, let's put xenon in the middle and put the fluorines around it and see how that goes. We have 4 times 7, 28, and 8 is 36. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I need to put 36 electrons in there. What the heck? Can I put extra electrons on fluorines? No, fluorines at period 3. Can xenon expand its octet and take more electrons? Yeah. Xenon's in period 5, period 5. I can do that. So I can put 2 lone pairs on the xenon. All of these fluorines have 0 formal charges. Let's look at the xenon. Xenon has 8 valence electrons. In this molecule, when we cut the bonds in half, it would leave with 8. It's got 0 formal charge. So that's the structure. Any questions about that one? Let's do H3PO4. So this one's going to be a lot like H2SO4. So we'll put the hydrogens off of the oxygens. And we count up electrons. Phosphorus has 5, and 3 H's. Hydrogens. 3 hydrogens is 3, and then 4 oxygens would be 24. So 8. That's what, 32? Yeah. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Great. You know, we got octets. We're good. Common mistake. This is not the correct Lewis structure for phosphoric acid. Look at the formal charges. Here's an oxygen with 2 bonds, oxygen with 2 bonds, oxygen with 2 bonds. They're all 0 formal charges. Oxygen with 1 bond. This guy has a formal charge. It brought 6 electrons. It would leave with 7, and so its formal charge is -1. What's the formal charge on the phosphorus? +1. It brought 5 electrons in, and when we break everything up, it leaves with 4. So if you think about, you know, the corporation or this business deal breaking up, phosphorus isn't going to be happy about this, right? It got shortchanged. So we have to find a way to put this together so that when we break it up, it comes out more even. That helps you think about it. This has a negative formal charge. Let's move one of its lone pairs to the phosphorus. And we can do that because phosphorus is in group 3. It can do an expanded octet. So if we do that, now this oxygen has 2 bonds. The phosphorus now has 5 bonds. Phosphorus brought in 5 electrons, and it takes half those bonds away with it, which is 5, 0 formal charges for everybody. Any questions?